So now we are solving trigonometric identities. So when we're solving equations, we're always asking the question, what will make the equation true? And not verifying, but solving so we can cross the equal sign and use the properties of equality that we have been using for years in algebra. So let's get started right away. Number one, cosine squared minus 2 cosine x equals 3. The first thing I see here is that this equation is quadratic. So we want to treat it as a quadratic, which means we want to set it equal to 0. So to set it equal to 0, we will move the 3 from the right over to the left. So cosine squared x minus 2 cosine x minus 3 equals 0. This sets us up to factor. So cosine x, a negative 3, and a positive 1. Once we have factored and we are set equal to 0, we're going to set each factor equal to 0, just like we did in algebra class. And this first factor yields the cosine of x equals 3. And the cosine of x is never going to equal 3. If you think about the unit circle, positive 1, negative 1, there we go. So why am I showing you this? Well, the range of the sine and the cosine goes from negative 1 to positive 1. So this particular value of 3 is out of the range. Therefore, that is an extraneous root. But on the other side, cosine x plus 1 equals 0, cosine x equals negative 1. We see where the cosine equals negative 1. Oh, excuse me, that's the sine. Let's look right over here. We've got an x value of negative 1, and that, of course, is at pi. And that is our answer. X equals pi. So only one solution there, but that's okay. We had an extraneous root. Remember, by definition, sine and cosine are opposite over hypotenuse or adjacent over hypotenuse. Therefore, the cosine of x can never actually be equal to 3. That is number one. Number two, a little bit more straightforward. We can easily isolate the trigonometric expression by dividing both sides by 4, which gives us sine squared x equals 1/4. We want to undo the square with an inverse operation, which of course is to take the square root. So we end up with sine x equals plus or minus the square root of 1 is 1, the square root of 4 is 2. Remember, once again, this is quadratic, therefore we do want to consider the positive and the negative. So let's draw a quick diagram here to help us figure this out. Where is the sign positive? The sign is positive in 1 and 2. And where is the sign negative? It's negative in 3 and 4. So we're going to have a solution in every one of the quadrants, everywhere where the sign is equal to 1/2. That is going to be everywhere where we have a 30-degree reference angle, or pi over 6. So 1 pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So x equals all of those solutions. And being that we're here, this, of course, is the list of specific solutions that exist within the slice of the domain from 0 to 2 pi. If we wanted to give the general solutions, of course, represent every possible solution. So let me label it. These are the specific solutions within a given domain, 0 to 2 pi. Or we can also give the general solutions, which are going to be in terms of a variable. So we'll say that variable is n, and n represents any complete number of revolutions. There we go. So when I say a revolution, I mean 360 degrees or 2 pi radians. So we could give this particular general solution. First of all, notice that pi over 6 and 7 pi over 6 are on opposite sides of the same pole. Yes, P-O-L-E. So one general solution is x equals pi over 6 plus, in this case, we only have to travel 1 pi, so pi times n. Another general solution would be for the other pole, this pole spanning between quadrant 2 and quadrant 4. So 5 pi over 6 plus pi times n. So specific solutions, 1, 2, 3, 4 of them within the domain slice, and then 2 general solutions. Remember, general solutions give us infinitely many solutions that might work, and that would be the general solutions. That's number 2. Number 3, one similar to like one we did in class, where we need to make a substitution, because right now we have an equation in terms of cosine and sine, and this is not helpful. So the hint I gave in class was this. First of all, move the 1 over and look at that middle term. That term that is to the first power there. So use that as your representative to let you know what you need to replace up front. So since I don't have a substitution for sine, I do have a substitution for cosine squared. So I'm going to plug in 1 minus sine squared in for that cosine squared. And now my whole equation will be in terms of sine. So we need to use the distributive property here, following order of operations. 2 minus 2 sine squared x minus sine x minus 1 equals 0. So 2 minus 1 is 1. So now we've got negative 2 sine squared x minus sine x plus 1 equals 0. The next thing that I would do would definitely be to get rid of the negative leading coefficient. The easiest way to do that is simply to divide both sides by negative 1, which will just flip all those signs. SIGNs. So 2 sine squared x plus sine x minus 1 equals 0. And then this will easily factor from here. So 2 sine x times sine x, a 1 and a 1. I want a positive in the middle, so plus, minus. There's my factors. Set each factor equal to 0. 2 sine x minus 1 equals 0. So sine x equals 1/2. There's the first factor. Sine x plus 1 equals 0. Sine x equals negative 1. From here, we can pretty quickly find our specific solutions. To find our specific solutions, where does the sine x equal negative 1/2? We just did this in the last problem. Of course, this is only positive this time, so it'll just be in quadrants 1 and 2. So first specific solutions are pi over 6 and 5 pi over 6, quadrants 1 and 2. And then where does the sine x equal negative 1? Sine equals negative 1 at the bottom of the unit circle at 3 pi over 2. So that is my third specific solution. Now this one's going to have lots of general solutions, because if we look at these locations, there's 1, and then of course here's pi over 6 and here's 5 pi over 6. Our general solutions are going to be plentiful. There's going to be 3 of them. So x equals pi over 6 plus 2 pi times n. Remember, n represents a number of revolutions, complete revolutions. There's the first one. 5 pi over 6. There's no way to do this shorthanded because these are not on the same pole and they're not on the same pole as this one. So let's write that last general solution right down here on the bottom. 3 pi over 2 plus 2 pi times n. 3 specific solutions, 3 general solutions for the equation 2 cosine squared x minus sine x equals 1.